Welcome back, ladies and gentlemen. So, last time we talked about the heat of solvation. We talked about breaking down of solute particles in a solvent. Today, we're going to be talking about the solvation process, or the making of a solution for ionic compounds, right? It's been so long since we saw our dear old friends ionic compounds, right? We started those in grade 10. We learned about how these metals, nonmetals came together. We learned about how strong the bonds are connecting them together. We learned about how incredibly hard it is to melt, boil, and all the rest of it, these ionic compounds. And now we're going to discover that they have a fundamental weakness. They have a fatal flaw. They dissolve in water. So, ionic compounds consist of a charged ion held together by electrostatic forces, aka ion-ion bonds. They are generally solid, crystalline structures at room temperature, and even higher than that. So, sodium chloride in salt dissolves in water. We've used that one about, 50 times at this point. Sodium chloride is the solute, water is the solvent, they come together. All of this we know very well. Where are we going with this? When a solute is placed in a solvent, the solvent particles completely surround the surface of the solute particles, okay? Again, the example we were using, talked about the markers, and we said, right, the bonds have to break, then reach and grab, and then make a new bond. But in order for that to happen, first, the water surrounds the solute, right? So the particles of water are ready to go. What does this do? Polar water molecules, remember that? Polar? What does polar mean? It means that one side is positive, one side's negative, or partially positive, partially negative. Polar water molecules orient or turn themselves around each exposed ion on the crystal surface, on the lattice of the solid. The positive end of the water molecules orient or turn themselves towards the negative chloride ion, the Cl-, right? Which side is the positive ones? I think we remember. I hope you remember. I hope you remember that hydrogen side of the water molecule is the positive side of the polar compound. The negative end of the water molecule then points towards the positive sodium ion, the Na+. What does this do? This. Right? The water molecules basically surround and gang up on each piece of the chlorine. They grab hold and they pull it away. This is one of the reasons why the solvent has to be in larger concentration, larger quantity than the solute, because that way it can do the whole surrounding thing. This is necessary because, again, remember, ionic interactions between full ions are very, very strong. The interaction between water and chloride here, chloride because it's an ion, these interactions are going to be weaker compared to the ones that we originally had. But there's more of them. And that overabundance, that increased amount of bonds and connections means that this is favorable. This will occur. But that only can happen if there's enough water to connect everybody. Here it is as an animation, right? The water comes in, they grab individual pieces and pull it away. This happens slowly over time, and this is the reason why a particular solute will dissolve one piece at a time, rather than all at once. Of course, as a result, you guys know this. We're going to talk about this in just like seconds from now, but come on, you know this, right? If you want to dissolve something in water, what's going to dissolve easier? A cube of sugar or a pile of sugar, right? The cube takes longer. The pile dissolves very quickly. You can also make it go faster by stirring it. But let's keep going. Let's keep going. We'll talk about this in some detail. If the solute is soluble, meaning that it can dissolve, the attraction between the solvent molecules and the solute ions gradually increases to the point where it finally exceeds the forces holding the ion in the crystal lattice. So again, one chlorine, one water comes over and it's like, I can't pull it out, right? It can't break it free because the ion-ion forces are too strong. But then more water shows up and they sort of dogpile this poor chlorine, and eventually they'll pull it away because there's enough of them. As a result, the solute ions become completely surrounded by the solvent molecules. They disappear, they dissolve. So, something like that. And again, it always requires multiple bonds, more connections. So there are 3 steps to the dissolving process for ions. Step number 1, the solvent particles must move apart to make room for the solute particles. This process requires energy to overcome the force of attraction between the various particles and thus takes energy, just like we talked about last time. Step 2, the solute particles must separate from the other particles. This process also requires energy, which again means it's endothermic. So the first 2 steps, as we discussed last time, pulling things apart takes energy. But then just like last time, step 3, when the particles move between the various solvent particles, when the chloride dissolves into the water, the force of attraction between the solute and solvent take hold and the particles snap together. And this releases much of the energy, being an exothermic step. Right? We talked about this part yesterday. We know this. Okay? So the separation of ions is called dissociation. This is where you take our solid mass of sodium chloride and we pull the pieces out and spread them around the whole thing. That is called dissociation. The process surrounding the solute particles with solvent particles is called solvation. So we dissociate the particles in order to separate them from the original solid, in this case because it's sodium chloride, and then we surround them with solvent, water in this case, and that is solvation. Make sense? I hope so. Okay, if the solvent is water, we call this process hydration because, of course, chemists have another name for water. Water is so special, right? We had different types of water named reactions all over the place, so we got it again. So this is where the solute particles are said to become hydrated. If you gain water, you become hydrated. If sodium chloride gains water, it becomes hydrated. All right, makes sense, hopefully. That one was so quick. We're going to keep going. We're going to do the next one. Solvation process for covalent compounds. The other half of the equation, right? Ionic we did, metal, non-metal. Covalent. Okay, well, let's think about this. Ionic compounds are, of course, polar. Well, they're ionic, but they have a positive and a negative side. Covalent compounds, what were they? Think back to physical properties of matter. I know it was a long time ago, but what do we remember? They were nonpolar. Some of them, of course, were more polar than others, right? We had that whole scale, that rainbow of color of different possible forces, but they were generally nonpolar, which means that we're going to have a different kind of reaction here. Take a look. When a covalent compounds are placed in a solvent, the entire molecule is pulled away from the solid structure. So what we're basically saying is, in the case of sodium chloride, the water could grab individual pieces and pull them out. In the case of a covalent compound, they can't, because there's nothing for them to really grab onto because of the whole nonpolar character. So what happens instead is that the water grabs the whole thing and moves it. And that's it. All right, to be fair, if I wanted to improve my analogy, I would say that the ionic ones were like this, where they were taking them apart and spreading them out, whereas the covalent would be like this, taking out the whole molecule all at once with it not taken apart. But, you know, analogies aren't always perfect the first time. There you go. You got a better one. Okay, so you'll notice we go from solid to aqueous down here. That's really the only difference. So things don't fall apart when they dissociate. When they dissociate from ionic compounds, right, they're going to break into pieces. So real quick, I probably should have mentioned this earlier, but I will do it now. When I dissociate, let's say, sodium chloride. It's solid to start with. I'm going to put it in water. I'm going to get Na plus AQ plus Cl minus AQ. So this is called a dissociation equation. It describes what happens when you basically break something down. But to be honest, this is basically a decomposition reaction just with water. So it's like a damp decomposition, basically, right? Because we're just taking something complicated-ish and we're breaking into two simpler things. Okay? Now, knowing my luck, that's going to be like on the next slide or something, so I just don't quite remember what's in my own slides, but let's see. Let's see. Is it the next thing? No, it's another animation. That's good. So here we go. We've got our individual particles, and they start to spread out, right? They're no longer in a clump, but they also didn't break down in any way. So we're going to start it over here. The water particles, they made them triangles. That seems weird, I know, but that's what they went with for this animation. And you can see they slowly but surely spread out among the entire solvent. Okay. Aqueous solutions and dissociation. We are on a roll. Let's do this. Aqueous solutions. Solutions in which water is the solvent are called aqueous solutions. We already talked about this before. We've talked about this in grade 10. I talked about this at the start of this whole unit. We've got this covered. They are common because water can dissolve many substances. Water is often called the universal solvent for this reason. So many things dissolve in water, it's almost kind of ridiculous, to be honest, right? When we want to clean things, we use water. Right? I don't see anybody lighting things on fire to clean them, although sometimes that also works. So dissociation is the separation of positive and negative ions, as we already discussed, and there's a dissociation equation, right? So the solid turns into two aqueous ions. You'll notice they're ions, right? Because remember, we have a full electron transfer with an ionic bond. You'll notice it's got water here sort of written above the line. That's a way to do it. It's to show that this whole thing is happening in liquid water. Reminder, we usually use L to mean that it is a pure material. AQ is when it's dissolved in water. When ionic compounds like sodium chloride dissolve in water, they no longer exist as a compound, but are freely moving as ions that are generally not associated with each other, right? So like, they're dance partners on the floor, but then the mob pulls them away, and they see each other in the distance, but they'll never get close again, at least not while the water's there. And as we discussed, a homogeneous solution, there's that word from the first lesson, a homogeneous solution can't be filtered by physical means because we don't have any filters that are small enough to stop the particles from getting through. All right, let's keep going. Molecular compounds like sugar do not separate into charged particles because they don't have any, but they dissolve as a whole molecule and therefore do not dissociate. So this goes from being a solid to being aqueous, as is, no change. Dissociation may occur when ionic compounds are in the molten state, melted at extremely high temperatures with no water at all, or in the aqueous state. So sodium and chloride ions dissociate as the water molecules surround them and pull them apart, just as we just discussed. A crystal of an ionic compound will not dissociate if the attractive forces in the crystal are stronger than the grip of the water. Right? I said, one water grabbing hold, it can't pull it out, right? And then we get like a bunch of them, and they eventually pull it out. I pulled two. Ruined the analogy already. That doesn't always work. What happens if the crystal is so strongly held together that it won't break apart? Right? Then it'll stay the way it is. But this is what I mean. This is the fundamental weakness of ions. Ion-ion interactions are incredibly strong, and yet, despite the fact that if I wanted to melt sodium chloride, I'd have to raise the temperature to more than 900 degrees Celsius, I think. If I wanted to break that salt apart, I could do it by just splashing a glass of water on it. It's strong, but it has a weakness. So, dissociation equations. See there, I did them earlier. I knew they were coming up. Write the equation for the dissolving solid of magnesium chloride, MgCl2, in water. So first, determine if the compound is ionic or molecular. MgCl2. It's ionic, molecular. It's ionic, right? It's got a metal and a non-metal. Second, write out the ions that will be formed by the dissociation. So Mg is 2+, Cl is 2-. Use the subscripts from the formula to indicate the coefficients that will balance the charge. Write the equation using the appropriate states of matter. Do I have an answer? No, I don't. Let's do an answer right now. All right, so here we go. We're going to have magnesium chloride, MgCl2, and it is solid. It is going to become Mg2+ plus Cl-. Now, you might be tempted to put Cl2 because because you're incredibly clever and have been paying attention this whole time, that chlorine is a diatomic gas. And it is a diatomic gas when it's on its own. And it needs an extra electron. And it's chlorine, not chloride. That negative there makes all the difference. Chloride doesn't care about sharing. It's got what it needs. It's done. So this is not Cl2. This is Cl-, completely different. But now I've got to balance this chemical equation, so there's going to be a 2 in front. Because again, remember, this is a damp dissociation equation, or a damp decomposition. That was what I called it. Because it's basically just decomposition where you make it wet first. Okay? This one here, this whole not Cl2, that's going to throw so many people. But that's because it's Cl minus. This minus sign changes the whole game. We know this, of course. There's a difference between atoms and ions. But people are going to be in a hurry. They're not going to be paying attention. They're going to be getting it confused because they remember it as a shortcut rule, not as an idea. It happens. And when it does, I promise not to laugh. Although I did laugh the one time when my students told me that water was this. That one caused me to laugh because I was dealing with grade 12 students that year, and I'm like, really? Grade 12 students, you guys got water wrong at this point? And they were all like, to be fair, Mr. C, that test was incredibly hard. And I was like, so hard you forgot what water was? And they were like, we're going to say yes, even though that doesn't make any sense in this context, but yes. Hopefully you guys don't get that bad. All right, so now you got some more practice that you guys can try. Give it a shot. You've got the answers, of course. See what you can do. Next time, we're going to be taking a look in more detail at polar versus non-polar, all right? But that'll be next time, and I'll see you guys then.